You're listening to Impulse to Innovation. The Institution of Mechanical Engineers podcast. I'm your host, Dr. Helen Mees. As a global community of mechanical engineers with over 120,000 members in 140 countries, the Institution of Mechanical Engineers has been at the heart of the engineering profession since 1847. The institution's mission is to improve the world through engineering by sharing the latest news, views and insight into the creative world of technology and the people that make it happen. This week, the 6th and 7th of March, sees the IMechE host its 4th Hydrogen Economy Conference in London. The international event will be focusing on infrastructure challenges as well as the storage and management of hydrogen as part of a wider green energy supply. Given the UK government's ambition for a decarbonised power sector by 2050, which will see the share of renewables in our generation mix increase significantly, a stable supply from these somewhat variable energy sources will become ever more important. The UK will therefore need substantial investment in its energy infrastructure to ensure that energy can be efficiently stored for days, months, or even years at a time. Engineers across the globe are looking at a range of technologies which will incorporate not only hydrogen, but compressed air, molten salts, and synthetic fuels to determine how energy could be stored in different forms or for different durations, ensuring that our energy requirements remain affordable, secure and stable while delivering on crucial emissions reductions. In this month's episode, I talk with Professor Tony Roskilly, Chair of Energy Systems at Durham University, about the future of energy supply decarbonisation and what engineers are doing to address the challenges of energy storage, management and infrastructure of clean energy sources. Professor Roskilly has over 30 years' experience in the design, control and operational optimisation of energy systems and energy management, and is a Fellow of the Institute of Marine Engineering, Science and Technology. He sits on the UK Government's Hydrogen Advisory Council Research and Innovation Working Group and is a member of the DFT Multimodal Hydrogen Transport Hub Board. Tony is also a co-director of the Durham Energy Institute, leading on industrial and internationalisation strategies, and is the UK representative for the European Energy Research Alliance's joint programmes for energy efficiency in industrial processes and energy systems integration. If that didn't fill all of Tony's time, he also leads the UK Hydrogen Fuel Transportation Network and is responsible for a large team at Durham University which leads national research on the decarbonisation of heating and cooling, focusing on the utilisation of solar, thermal and geothermal energy, thermal energy recovery, storage and utilisation, and energy system integration. Tony, thank you so much for joining me on today's podcast. It's a real pleasure to have you. As I mentioned in my introduction, you are Chair of Energy Systems and a co-director of the Durham Energy Institute. But among your many responsibilities, you also lead one of the largest research groups at Durham University, which heads up national research on the decarbonisation of heating and cooling. That's kind of roughly in a nutshell, I think. Can you tell us a little bit about the purpose of that research and what it hopes to achieve?
Yeah, so around 50% of our energy demand in the UK is in heating and cooling. And around 60% of that is used for space heating and hot water.
Yeah.
So the demand is very, very large. It's around five times greater than our electricity use. And that's just looking at it from a kind of domestic perspective. And the demands from industry and from commercial buildings, etc., kind of adds to the amount of energy that is required. And primarily that is met by natural gas.
Yeah.
And obviously that isn't sustainable going forward. And in the long term, we have to transition away from the use of fossil fuels. So the scale of the problem is enormous, and we need to kind of decarbonize as quickly as we can. And a lot of our research work is focusing on domestic, on commercial, on industrial heating and cooling, and coming up with solutions to rapidly, transition away from the use of fossil fuels, improve the overall efficiency of energy use, and going also beyond the UK.
Right.
We're focused on obviously our technology and our research, and that feeds into the UK scenario. But we have a lot of heating demand. We have an increasing amount of cooling demand, but in other countries, it's the other way around. They have a massive cooling demand and a very little heating demand. So, again, the technology that we're producing and the research we're doing is not only entirely focused on the UK scenario.
You're absolutely right. I mean, our behaviour here in the UK is going to be very different from somewhere like Africa or India. So what kinds of technologies are you looking at from that point of view then? How are you adapting ideas that perhaps we would use in the West for other countries?
Yeah. So, as I say, we're working on solutions to decarbonize and increase the efficiency of heating and cooling, and also humidity control.
Right.
That's often something that is forgotten about and not looked at, but that contributes enormously to the energy demand within residential, commercial, and industrial environments. So we focus on that kind of holistically. We're developing technology to recover and use low-grade heat. So that could be from a solar thermal source, it could be from geothermal, it could be from surplus heat from an industrial process or a system. And we utilize that heat. We've been developing sorption technology, for example, to effectively store that energy and store renewable electricity in the same system,
right,
and to store it indefinitely and recover it in the form of either higher temperature heat or cooling or in electrical power in the same kind of system.
Yeah.
So, for example, we can recover low-grade heat from an industrial process, say at 80 degrees C, and we can produce cooling at minus 20 degrees C from that, or at a higher temperature at, say, 130 degrees C.
Right.
So there are kind of a number of applications where that technology would be useful, and across many different industrial sectors. We've been developing new thermochemical systems for seasonal storage of thermal energy. Right. So thermochemical systems that are more kind of energy dense than compared to conventional sensible heat storage like water tanks, etc., or even using phase change materials, so much more energy dense than that. And exploring them and demonstrating them to be able to store solar thermal energy, geothermal energy when it's not needed, say in the summer, and then release it and utilize it in the winter when it's needed.
Right.
So we're doing a lot of work around there, a lot of work around adaptive climate control, using thermochemical fluids for controlling the temperature and the humidity in a number of examples, say in greenhouses, in glass houses, growing crops, for example. Right, yeah. Humidity control is really important. In painting cars, the vast majority of energy that goes into manufacturing a car is painting it. And that heating process, that humidity control, the painting process is really finely controlled, and that environment takes a lot of energy to control, and then you cool it to be able to then work on the car. Right. So our technology will drastically reduce the energy required to provide that kind of that environment, that the optimum environment inside a paint booth, for example.
I never even considered that was something that you would be able to do, actually. That's really insightful. And it kind of leads me on to my next question, actually, Tony, because last year the IMechE published its report on adaptation to rising temperatures and the role engineers will have in finding innovative ways of improving energy efficiency and particularly cooling as well in both residential and industrial environments. So what kinds of technology, and you've kind of touched on it there, are being developed to manage heat more effectively? And I'm curious as well as to how industrial clusters, for example, will contribute or to and benefit from these kind of thermal management sort of systems or schemes that you've just been talking about.
Yeah. So more and more, the way that improvements are going to be made is thinking about it as an energy system rather than individual components. For example, there are very often the paint shop, for example, for car manufacturers is a clear example of that. There is a lot of gas that goes into heating the body when the coating is made, and then enormous amounts of electricity input to cool it. For it to be then worked on. And that combination of where you've got heat and surplus heat and a cooling requirement, you can offset the cooling requirement by utilizing that waste heat. And that's what we developed technology to be able to do that. A lot of climate control within swimming pools. Swimming pools, for example, are finding it really difficult to cope with their energy costs.
Yeah.
And they have heating and humidity problems. Gyms are the same kind of thing. So if you can actually integrate a system to be able to cope with both temperature and humidity, that has kind of major advantages in terms of the overall efficiency, energy efficiency of the system. A conventional humidity control system actually has a lot of energy going in to overcool, to remove the moisture content, and then heating it back up to the required temperature. Yeah. If you control it using thermochemical fluids, then you don't need to put that additional energy into the system. In terms of the kind of industry, so I work very closely with Teesside Industrial Cluster and with the other clusters. And obviously the challenge is enormous to decarbonize. And a lot of the effort is going quite rightly in increasing the efficiency of operations, of processes, and the utilization of energy. The greater use of electrification, if and where it's possible to do, but more increasingly the role that hydrogen would play in decarbonizing the activity, not just as a feedstock within chemical processing, but actually as a way to provide the high temperatures that are required for many processes.
Do you think, in terms of those industrial clusters as well, that we've got the space to be able to put in some of this new infrastructure? Because a lot, as you're talking about Teesside and the northeast, but many of the major cities where the big industrial centres don't really have the land available. Are we going to have to rebuild some of these areas, or do we have the capacity to be able to install these kind of new systems?
I think within the industrial clusters, I think there is the redevelopment of land, the repurposing of areas that are making way for kind of the new sectors, the new technologies. There are a lot of plans, for example, advanced plans for electrolyzers within industrial clusters, the production of hydrogen for use to help decarbonize. I think that all the industrial clusters have their strategies and their plans, and to a certain degree, there's a mixture of greater electrification, alternative hydrogen fuel carriers, hydrogen in its own right, the use of new fuels that will feed into the industrial cluster.
That sounds like it's going to be quite a major task, but equally, I suppose it's an opportunity to not just develop new technology for industry, but also that will trickle down into kind of the residential, more societal kind of systems as well. I'm guessing that one driver will be to kind of push some of the new builds for housing estates and things like that to include some of this kind of technology, would it be?
Yes. So, as an example, we have a concept that we've been working on for some time, looking at hydrogen energy hub and providing 5 energy services from the utilization of hydrogen in its most efficient and effective way. So, in terms of providing heating, cooling, electrical power, rapid EV charging, and refueling of hydrogen vehicles. All of those 5 energy services can be provided in an optimum way through the use of hydrogen. And that has applications in an industrial setting, and we're exploring that within an industrial setting. It has potential for an energy center for a hospital complex, for example,
Right, yeah.
or in individual residential areas, rather than hydrogen being supplied to every individual home from a point of view heating perspective. If you had a system where you had energy hubs that were providing heating through heating networks or cooling networks or local power grids, for example, you can maximize the overall efficiency of using hydrogen in that way. So a lot of our technologies in terms of thermal energy storage, we've been working on thermochemical systems to store the heat that is incident on the roof of our houses and to store that seasonally and then utilize it in winter.
Right.
We've looked at studies for individual houses, for high-rise flats, for industrial applications. Again, there are different applications that would require a little bit more work to be done, research to be done to increase the energy density. But for certain applications, then we already have solutions that could provide that seasonal storage.
Yeah, because I'd always assumed that hydrogen, and I know that this is an area that is of particular interest to you, Tony. I'd always assumed that it was kind of one of those fuels that would be more useful in the industrial setting. But I understand that there are scale demonstrators, aren't there, being tested in terms of residential applications. And I think there's some work being done in Germany as well to look at power to hydrogen, hydrogen to power conversion. But as I understand it, there's concern that there's quite a lot of inefficiency in that process. So can you tell us a little bit about what that concept entails and what sort of problems engineers are going to have to overcome to address those inefficiencies?
Yeah, so this inefficiency, to a certain extent, is a misconception, and I think it's because people are concentrating on individual components.
Right.
So they're concentrating on the conversion of electricity to hydrogen through electrolysis and the losses associated with that. They're talking about the use of hydrogen to then in, say, a fuel cell, for example, to produce electricity and the losses associated with that. So the vast majority of the losses in those processes are always in the form of low-grade heat.
Okay.
And if you can utilize that low-grade heat, then in a system approach, and adopt a system approach, then the overall efficiency is high. So as my example for this energy hub, if we're actually utilizing the surplus heat that is produced from those conversion processes and utilizing that within heat networks or driving using heat to drive a cooling network, you're able to kind of maximize and get very, very high efficiency overall.
Right.
It's in a similar way that combined heat and power systems have very high overall efficiency if you have a use and can utilize the heat from that conversion process to produce electricity. So that's why kind of looking at it from a system perspective and looking at these energy hubs, and that leads itself to more distributed kind of energy services provided, so that you're embedded where there are more than one demand.
Yeah.
There's a requirement for heating, or there's a requirement for cooling as well as electricity.
Yeah, that makes total sense. It's not a case of just plonking in a piece of technology and expecting it to work, but we have to think about the whole system, what the environment is that we're putting it into. Absolutely. And that's a real driver, I guess, for a lot of engineers, is to ensure that it's applicable to the environment that it's been put in, right?
Yeah.
Now, one of the biggest challenges that stands out to me is storage. National Grid have forecast that we're going to need somewhere up to about 29 gigawatts of storage by 2030 and up to 51 gigawatts by 2050. That's a huge increase on I think it's roughly about 5 gigawatts of storage that we have now in the system. So how on earth are we going to achieve that in the long term? And what kinds of storage mediums are we going to be using in order to store this kind of energy?
So I guess these figures have been derived from estimations around the variability of renewable energy on the grid,
right,
and also the increased use of electricity for transport applications, building and industry. So the greater electrification of take up of heat pumps, for example, and EVs, etc. As you would imagine, from my previous answers, I think that there should be more focus on thermal storage and also a better thermal management, not just for heating and cooling, but also of power generation.
Yeah,
integration of the system to maximize the efficiency and also to really think about increased resilience. And again, very often resilience in our energy system is not really been much of a focus on. Putting all of our eggs in one basket is potentially a recipe for disaster. But in terms of electricity demand, so that could be further reduced. So I think there is enormous potential for energy demand reduction. And sure, kind of inroads will be made through the utilization of battery storage.
Yeah.
Some other grid-scale energy storage technologies. We were at the forefront of developing a grid-scale energy storage system. Again, but it's very slow progress on that front. There are viable options. It's just getting the investment to actually scale up is a huge challenge. But going back to hydrogen, so we think of it as a fuel, but it's a store of energy. And actually, if we utilize that stored hydrogen for power generation and provide dispatchable power to balance the grid, then that will offset the requirement for any other forms of storage. So I think the answer is that we need all that we can get. Any technology that can scale up rapidly, that's what we need. And I don't think there's one, almost with any of these energy challenges that we face, there is no one silver bullet. There's not one solution. We need to work on every aspect to improve our situation going forward.
Yeah, I mean, going back to what you said right at the start, every country is going to be different, even different locations in different countries, particularly where you've got the size of Africa or Australia, for example, are going to need different sorts of systems, aren't they? And so we need to be prepared for all of those. I guess we're at that point, aren't we, Tony, where this is a great opportunity to try new systems, to try new ideas and innovations, so that we can draw from the best of all of these, rather than just, as you said, putting all our eggs in one basket.
Yes, I mean, so at the moment there's a lot of debate around which fuel will be the winner in a sense. So, hydrogen, methanol, ammonia. We've actually spun out technology, it's a power generation system that is fuel flexible.
Right.
So it will work and produce power and switch between say hydrogen to methanol back to hydrogen again without stopping, so that you're not got a situation where you've got stranded assets.
Yes.
Putting all of your eggs in one basket to say, okay, we're going to be able to invest in new equipment that's going to provide power fueled from methanol, for example. But the availability of e-methanol going forward is still an unknown. How quickly that will be scaled up is anybody's guess. So we have to be be resilient to all of the options. We're in a transition, and we have to remember that we're in a transition. We can't just switch on immediately to a decarbonised world. We have to get there in an economically viable way.
Yeah, I would agree with that. And living in very rural Lincolnshire, as I do, with fields and fields of solar panels out to the west of us, there has to be some stability in the system, doesn't there? There has to be ways of storing in different ways so that we can maintain that stability, not just industry, but for society as a whole.
And also to utilise that energy when it's not required.
Yeah.
So, when electricity demand is low, but it's blowing a gale, and we have a lot of wind resource, or we have a lot of solar resource, we need to be able to maximise that and maximise that investment in that infrastructure to the optimum, and that's where hydrogen fits into that scenario.
Well, I'm very keen to see how the hydrogen economy grows over the next few years, and it's certainly an area that I know the IMechE members are particularly interested in focusing on. So we'll see how that goes on. I'm very excited at the moment because actually, as we speak, we're having solar panels fitted to our house roof, and we're having storage batteries fitted as well. So I'm quite excited to see my little contribution to the system and how that will work in the coming years. Last July, the House of Lords Science and Technology Committee launched an inquiry into long duration energy storage. And you've kind of mentioned it a little bit while we've been talking. Storing energy over long periods of time, it kind of makes complete sense to me. I mean, it seems obvious, really, as an engineer, but it's still very much in its infancy, I guess. So is long duration energy storage a viable option, in your opinion? I suspect it probably is. But should we be looking elsewhere for more achievable solutions in the short term? Is this a long-term thing that we need to invest in?
Yeah, so long-term storage. So again, I think hydrogen fits within that mix. I think storage in hydrogen carriers, for example, ammonia. But in terms of electricity side of things, then there are kind of a number of solutions or technologies that are being developed around Carnot battery technology, pumped heat energy storage, which was a system that my research team have done a lot of research on and have further kind of concepts that we're working on. Compressed air energy storage. There's a whole kind of range of mix, and they've all got their own pros and cons associated with them. At the end of the day, it's kind of the economics that kind of determines whether any large-scale, grid-scale energy storage system takes off. And that is tricky. And I think everything that we've been talking about in terms of decarbonisation, there is a cost associated with it.
Yeah.
And that having to be factored in is something that is really, really important. There is a cost associated with the reduction of CO2 emissions. There's a cost associated with the transitioning to adopting technologies to decarbonise. But I think that is happening. I think the other slight problem here is that who rewards first movers, and that it cuts up in a lot of conversations that I have, particularly with the maritime sector. And I think that there are some technologies there. It's the cost associated with the scale up, because when we're talking about megawatts and gigawatt, that we're talking about millions of pounds of investment to be able to take these technologies forward. We have solutions that are already viable. It's just the investment in making them happen.
So do you think as engineers we've got a lot of work to do then in terms of convincing the likes of government, the purse holders, if you like, that this is beneficial for the long term, even though it will potentially add cost to our energy prices, for example, or things like that. This is really what we need to be investing in now, because we're just not ready for the climate changes that we're already seeing.
Yeah, so I think from an engineer's perspective, in developing technology, we have to think a lot more about the capital cost and the operational cost.
Yeah.
As a research engineer, a lot of my life has been working on increasing efficiency. We come back to that term efficiency.
Yeah.
You know, this drive to increase efficiency by 2% or something. If the technology is about 4 or 5 times more expensive, then it's not economically viable to be taken up and deployed.
Yeah.
So I think we have to kind of again take a system approach, looking at the overall efficiency and exergy associated with a energy system, and also looking at its capital cost and its operational cost. We can do a lot of work on reducing capital cost. We can do a lot of work around reducing operational costs. And that will actually make the take-up of these types of technologies quicker, rather than kind of striving for optimum efficiency, for example.
Yeah, I think we have, as an engineering community, a lot of work to do to educate non-scientists, particularly those in the finance sector, about the cost benefits of many of these pieces of technology and why we would recommend some over others. And I think there's something to be said there about why we need to be driving this change within government and the strategic part of our energy supply in the coming years. So I think that's a very important point to make, Tony. Thank you. I wanted to ask you a little bit about your passion for maritime decarbonisation, because I know that this is something that's very close to your heart. Maritime activities are the largest source of carbon emissions in the UK transport sector, as I understand it. And it's estimated to be somewhere in the region of £75 billion required over the next 30 years to transition the sector into a net zero state. I know you at Durham are working with a lot of other universities, about 13 universities and over 70 industrial partners to look at fuels and ship propulsion, as well as the port infrastructure as well. You talked about systems, and that's fundamental to driving marine change. A 2050 net zero goal. Do you not think that's rather ambitious for an island nation such as the UK? We've got a lot of coasts, right, to deal with. Do you think it's achievable?
I think that it certainly is a major challenge, and that's why shipping was left out of the original declarations on reducing emissions and reducing the impact on the environment. But now it's kind of front and center. It, along with aviation, it's one of the hardest sectors to decarbonize. By its very nature, it's international, it's global. It's, we trade across the world. Over 80% of all of everything that we touch, we eat, we see, has been on a ship at any one time. So you can get away from it. If we want to decarbonize everything, we have to decarbonize everything within the supply chain, and shipping goods and commodities, etc., are embedded in that. I drive an electric vehicle. I can't pat myself on the back because the steel has got embedded carbon in it. It was transported by ship to this country with a ship that was almost certainly using heavy fuel oil. So unless we decarbonize the whole side of the supply chain, that's what we have to do. And so shipping is really crucial in that. So from a point of view of our own kind of coastal shipping and our kind of own maritime activity, I think we can make really very, very rapid strides in that area. We have to really portray ourselves. We have to be a leader for the rest of the world and show leadership in this area. and provide some solutions. We need to provide solutions and work internationally on solutions. So we need to move towards new maritime fuels. So fuel switching is really key to the decarbonisation. So ammonia, hydrogen, methanol, these are fuels that have to be produced in a sustainable way. With hydrogen at the heart of those fuels. We need to be able to use them in a safe and efficient way. We have to, and it's not just the ships themselves, it's the ports. Ports only exist to service the ships that are providing the transport of goods. And it's not all about decarbonisation as well. It's about air quality.
Yeah.
So enormous amounts of air pollution associated with our port operations, in terms of particulate emissions, NOx emissions, all of those have to be dealt with, as well as the reduction of CO2. We are working on new propulsion systems. We're working on the decarbonisation of ports, and ports being energy providers in their own right, providing shoreside power to vessels so that they're not polluting when they're in port, to improve the efficiency and the utilisation of new fuels, of the infrastructure that ports use, improving the efficiency of vessels, reducing their energy demand through adoption of different technologies, but also exploiting digitalization and big data and machine learning to improve the logistics of how we operate and move goods via shipping. All of that's going to have a big impact and a way that we can hopefully very quickly reduce our emissions associated with the maritime sector.
It sounds fascinating that there's so much more than just dealing with the ships themselves, and it gives us a great opportunity, doesn't it, to come full circle in our conversation today, that we can learn that can be used in other sectors as well as trickling down into kind of the residential market as well. So it sounds to me like whilst it's going to be, yes, a very big challenge, there's actually an awful lot we can learn in the process in terms of the systems approach to solving the decarbonisation issue. Tony, thank you so much for joining me today. It's been a pleasure to have you on the podcast, to hear about some of these new technologies and new ideas that are being developed, and to see how it's been applied. I think that's for me the really big thing. There's so much talk in this sector, isn't there, about what we could do, but what I'm hearing from you is that this is really here now, and we can get this done, and the technology is being developed. So thank you very much for sharing that with me today.
Thank you.
That's all for this month. In next month's episode, we'll be exploring traffic management, how major cities around the world are handling the increasing number of vehicles on the road, and how rural communities are requiring greater access to public transport. We will also be looking at MaaS, mobility as a service, and what, if anything, it can achieve. You've been listening to Impulse to Innovation, the Institution of Mechanical Engineers podcast. Thanks for listening. We'd love to hear from you, so if you'd like to share any news or any feedback with us, then please email us, podcast@imeche.org. All the information on this episode can be found in the episode notes.